Hello students, welcome to EPG Pathshala. I am Professor P.N. Kodru from Jammu. Today we are going to discuss about a module entitled The Reciprocal Lattice under paper Crystallography and Crystal Growth. So students, let us see what we are going to learn in this module. We are going to learn about the concept of reciprocal points, direct and reciprocal lattice. We are going to talk about mathematical description of a reciprocal lattice. We will derive a relationship of reciprocal lattice axes and direct lattice axes. We shall also talk about reciprocity between direct and reciprocal lattices. Now let us first take up the reciprocal lattice. In crystallography, a set of parallel planes with the same interplanar spacing between them are treated as equivalent and as such are represented by the same indices. A two-dimensional plane can very easily be represented by its normal. The direction of normal indicates the orientation of the plane. So if planes are represented by their normal, it becomes easier to visualize one-dimensional normals as compared to two-dimensional planes. Both orientation of planes with respect to crystallographic axes and their interplanar spacings are of interest to the crystallographers. This gave rise to a new concept known as the reciprocal lattice. Let us take into consideration any given space lattice. Select any lattice point on the origin and draw normal to different planes. At each of these normals, a point is taken at such a distance from the origin which is proportional to the reciprocal of interplanar spacing, that is proportional to 1 upon small d, where small d is the interplanar spacing. The single point so drawn on the normal represents a set of parallel planes of a particular orientation and interplanar spacing. This point is known as a reciprocal point. The reciprocal points, which are the terminal points of the normals to all the sets of lattice planes from a lattice, and so are called reciprocal lattice points. Therefore, we have two types of lattices. One, the direct lattice, and the other, the reciprocal lattice. The direct lattice is Bravais lattice, which, as already explained, is described by the positions of the lattice points corresponding to the positions of atoms or molecules. The other type of lattice, which is constructed from lattice points, is the reciprocal lattice. Mathematical description of a reciprocal lattice. In this section, we will find the relationship between direct and reciprocal lattices. In doing so, we may consider the direct crystal lattice, whose unit cell is described in terms of the vectors A, B, and C as shown in figure 12.1. Volume V of the unit cell is given by V equal to area of base small o b f c into height, which comes out to be capital A into capital O capital M. Using vector algebra, the area A is equal to small b vector cross small c vector. So capital V is equal to small a vector into b cross c, which is equation number 12.1. The spacing of the BC plane is given by the height OM. Let us represent the interplanar spacing of the plane as D100. So V will be equal to capital A into D100. In vector notation, the normal to a plane is shown by the unit vector small n. Sigma HKL is equal to 1 upon D100 into n vector, which is equal to capital A by capital V and given as equation number 12.2. Since an area is represented by the vector product of its sides, 1 upon D100 into n vector is equal to B cross C upon capital V. Substituting from equation 12.1 for capital V, we get 1 upon D100 dot n vector is equal to B cross C upon A dot B cross C, which is represented as equation 12.3, where n vector is the unit vector normal to the BC plane shown as shaded in the figure, that is along A star. It may be noted that in the construction of reciprocal lattice, to each plane HKL of the crystal, a normal is drawn of length sigma HKL, which is equal to the reciprocal of interplanar spacing, so that sigma HKL is equal to 1 upon DHKL. By definition, A star may be expressed as modulus A star vector is equal to modulus D star 100 vector is equal to sigma upon D100, which is represented as equation 12.4. A star vector is equal to D star 100 vector equal to sigma into n vector upon D100, which is given as equation 12.5. On substitution from equation 12.3 for n upon D100 in equation 12.5, we get A star vector equal to D star vector is equal to sigma into B cross C upon A into B cross C, which is given as equation 12.6. Following a similar procedure, one can show that D star 010 vector is equal to B star vector is equal to sigma into C cross A upon A cross B cross C, which is given as equation 12.7, and D star 001 vector is equal to C star vector is equal to sigma into A vector cross B vector upon A vector into B vector cross C vector, which is given as equation 12.8. The magnification factor sigma is given different values in different applications of the reciprocal lattice. In this particular case, let us put sigma equal to 1. Equations 12.6, 12.7 and 12.8 can then be written as D star 100 vector is equal to A star vector is equal to B vector cross C vector upon A vector into B vector cross C vector, which is given as equation 12.9. Similarly, D star 010 vector is equal to B star vector is equal to C vector cross A vector upon A vector into B cross C, which is given as equation 12.10. D star 001 vector is equal to C star vector is equal to A cross B upon A vector into B vector cross C vector, which is given as equation 12.11. Equations 12.9, 12.10 and 12.11 express reciprocal lattice vectors in terms of the direct lattice vectors. The reciprocal axes are related to crystal axes, which can be easily deduced from the vector notation of equations 12.9, 12.10, and 12.11. The relations are: A star vector is normal to B vector and C vector, given as equation 12.12. B star vector is normal to C vector and A vector, given as equation number 12.13. C star vector is normal to A vector and B vector, which is given as equation 12.14. Equations 12.12, 12.13 and 12.14 can be easily derived as follows. Let us take the dot product of A star vector and A vector. From equations 12.9, 12.10 and 12.11, we have A star vector dot A vector equal to B vector cross C vector upon A vector dot B cross C into A vector, which is equal to 1, and put as equation 12.15. Similarly, B star vector dot B vector is equal to C vector cross A vector upon A vector dot B cross C vectors dot B vector is equal to 1, which is equation 12.16. C star vector dot C vector is equal to A vector cross B vector upon A vector into B cross C vectors dot C vector is equal to 1, which is 12.17. Taking dot product of A star vector with B vector and C vector, we have from equations 12.9, 12.10 and 12.11 A star vector dot B vector equal to B vector cross C vector upon A vector dot of B vector cross C vector dot B vector, put it as equation 12.18. A star vector dot C vector is equal to B vector cross C vector upon A vector dot B vector cross C vector dot C vector, put it as equation number 12.19. We know that B vector cross C vector is a vector at right angles to both B vector and C vector, and therefore following vector algebra, the left-hand side of equations 12.18 and 12.19 are 0. So, A star vector dot B vector is equal to 0 and A star vector dot C vector is equal to 0, which is referred as equation 12.20. In the same manner, one can show that B star vector dot C vector is equal to 0 and B star vector dot A vector is equal to 0, which is put as equation 12.21. C star vector dot A vector is equal to 0 and C star vector dot B vector is equal to 0, which is equation 12.22. Thus, from equations 12.20, 12.21 and 12.22, we obtain the following results. A star vector is normal to B vector and C vector, given as equation number 12.23. B star vector is normal to A vector and C vector, given as equation 12.24. C star vector is normal to A vector and B vector, which is given as equation 12.25. Equations 12.23, 12.24 and 12.25 suggest that A star axis is normal to BC plane, B star axis is normal to AC plane, and C star axis normal to AB plane. If we look at the expressions 12.23, 12.24 and 12.25, one can deduce that A axis is normal to B star axis and C star axis, or in other words, A axis is normal to the B star axis as well as to C star axis. Expressions number 12.24 and 12.25. Similarly, B axis is normal to A star and C star axes. Equations 12.24 and 12.25. Also, C axis is normal to both A star and B star axes as represented by equations 12.23 and 12.24. To summarize the above deduction, one may state the following. A is normal to B star and C star axes. Let us put it as equation 12.26. B is normal to A star and C star axes. Let us put it as equation 12.27. Similarly, C is normal to A star and B star axes. Let us put it as equation 12.28. Equations 12.26 to 12.28 suggest that A is normal to the B star C star plane. B is normal to the A star C star plane, and C is normal to A star B star plane. Equations 12.23 to 12.25 and 12.26 to 12.28 establish the fact that there is complete reciprocity between the reciprocal and direct lattices. Any reciprocal lattice vector D star HKL is related to unit translations of this lattice as denoted by A star, B star and C star by the expression D star HKL vector is equal to H A star vector plus K B star vector plus L C star vector, which is put as equation 12.29. It means that to reach a reciprocal lattice point HKL, one has to go H units along A star axis, K units along the B star axis, and L units along the C star axis. According to it, the indices of the reciprocal lattice point correspond to their coordinates along the A star, B star, and C star axes. Let us consider the lattice plane HKL. It intercepts the axes A, B, and C at A by H, B by K, and C by L respectively, as shown in figure 12.2. Figure 12.2 shows lattice plane HKL intercepting the axes A, B, and C at A by H, B by K, and C by L. OA vector is equal to A vector by H. OB vector is equal to B vector by K. OC vector is equal to C vector by L. All these are put as equation number 12.30. Now, AB vector is equal to B vector by K minus A vector by H. And BC vector is equal to C vector by L minus B vector by K, and AC vector is equal to C vector by L minus A vector by H, which is put as equation 12.31. Taking the dot product of D star HKL vector, AB vector, and using equation 12.29, we have D star HKL vector dot AB vector equal to HA star vector plus KB star vector plus LC star vector dot B vector by K minus A vector by H, which is equal to h by k a star vector dot b vector plus b star vector dot b vector plus L by k c star vector dot b vector minus a star vector a vector plus h by k b star vector dot a vector plus L by h c star vector dot a vector, which is equation 12.32. Using equations 12.15 dash 12.17 and 12.20 dash 12.22, we have d star hkl vector dot of ab vector is equal to h by k cross 0 plus k cross 1 plus L by k cross 0 minus 1 plus h by k cross 0 plus 1 by h cross 0, which is equal to 1 minus 1. That comes out to be equal to 0. That means d star hkl vector is perpendicular to ab vector. Similarly, we can show that d star hkl vector dot of bc vector is equal to 0, or d star hkl vector is normal to both ab vector as well as bc vector. It means that it is normal to the plane containing AB and BC, and so to the plane ABC, which carries indices HKL. So one can conclude that D star HKL vector is normal to HKL plane. Let n vector be unit vector perpendicular to ABC from the origin at O, which leads to an expression d star HKL vector is equal to modulus d star HKL vector into n vector is equal to h a star vector plus k b star vector plus l c star vector, which is equation number 12.33. Interplanar spacing of crystal lattice. From equation 12.33, we have n vector equal to h into a vector, a star vector plus k b star vector by modulus of d star hkl plus l c star vector, given as equation 12.34. The length of interplanar spacing of the plane shown in the figure 12.1 and represented by OD in figure 12.2 is given by OD minus B by K into cos phi, where phi is the angle between OD and OB. DHKL is equal to A by H cos phi, which is equal to A vector by H into N vector, given as equation 12.35. Using equation 12.34 for n vector, we have DHKL equal to A vector by H into H A star vector plus K B star vector plus L C star vector upon modulus of D star HKL vector, which is equal to A vector dot A star vector plus K by H, A vector B star vector plus L by H, A vector dot C star vector upon modulus D star HKL vector, which is given as equation 12.36. Using equations 12.12, 12.24 and 12.25, we have DHKL is equal to 1 plus 0 plus 0 upon modulus D star HKL vector, or D star HKL modulus is equal to 1 upon DHKL, which is given as equation number 12.37. That is, D star HKL is perpendicular to HKL and its magnitude is 1 upon DHKL. Relationship of reciprocal lattice axes and direct lattice axes. Let A, B, C represent direct lattice parameters and A star, B star, C star as the reciprocal lattice parameters. Also let alpha, beta, gamma be the interaxial angles for the direct lattice and alpha star, B star, gamma star for the reciprocal lattice. Considering reciprocity between direct lattice and reciprocal lattice as explained earlier, and on the pattern of equations 12.15, 12.16 and 12.17, we have A vector equal to B star vector cross C star vector upon A star vector dot B star vector cross C star vector, given as equation 12.38. Similarly, B vector is equal to C star vector cross A star vector upon A star vector dot B star vector cross C star vector, which is equation 12.39. C vector is equal to A star vector cross B star vector upon A star vector dot of B star vector cross C star vector, which is given as equation 12.40. Equations 12.38 to 12.40 are the relationship of reciprocal lattice axes and the direct lattice axes. So students, let us summarize what we have learned in this module. The reciprocal lattice has been described and discussed. The mathematical description of reciprocal lattice is given. The relationship of reciprocal lattice and direct lattice axes is explained. The equations establishing complete reciprocity between the reciprocal and direct lattices are obtained. Also, the expressions relating reciprocal lattice axes and direct lattice axes are derived. Thank you.